Yeah. Okay, I think it's all right, guys. I think I'll go ahead and get started. There may be some more people coming, and also in Zoom. We'll see. But I am recording this, and I'm going to put it up in YouTube and send you guys a email link with the video also. So if you need to leave early or you just need to watch something again later, you're certainly going to be able to do that. Um, just a reminder, I have office hours later on after the review session from 4 to 5, and then also this evening after this event I have to go to. But I should be back by 8 or 9, and then I'll be in tomorrow around 10. And everything should be up to date in Canvas right now, in particular the review packet, which I'm sure you guys have been looking at. So feel free to go through that. And those double starred items, those are the results that have relatively short proofs that would be good to look over. I mean, I hesitate to use the word memorize because that's a lot to memorize. It's more of a getting sort of the idea behind the proof. So like, how would you prove that a differentiable function is always continuous? Well, we would need to prove that f is continuous by using like the huge remark or something like that. And then setting that up in terms of writing down the definition of the derivative and what differentiable means and so on. So just those kinds of things I think are pretty helpful. So, hi Maria, can you see me and hear me okay?
Yes.
Okay, perfect, great. Yeah, so anyway, and there's a few problems in the review packet. I think we essentially did one of them yesterday in the group work, but there's a couple more problems there that might be worth looking at. Oh, I'm going to do another one of them right now as well. So there won't be that much. The main thing at this point is if you haven't looked at the sample test, I would do that by tonight for sure, so that if there's any issues that come up, you can get it figured out by tomorrow if you have any questions like that. So what I'm going to do for the next couple hours is do some more practice problems, and this will just be building off of what we already did last time. So I'm going to just continue my numbering from where I left off, and it's just going to be kind of a hodgepodge of random examples that I think are not too hard, not too easy, somewhere kind of in the middle of the sweet spot of what I think would make good questions for the exam. So let's do that. Let's just jump in, and I will just kind of mix up the topics a little bit as I did the other day as well. I think we're on number 7. Is that right?
Mm-hmm.
Yeah. Okay. So we're picking up where we left off from last time. So here is the problem. Let's suppose that f is a function from a domain D to the real numbers R that is uniformly continuous. So if this was going to actually be a question on the test, I probably would start by asking you in part A to define uniform continuity on a domain D. So that knowing the definition of that would be kind of part of this as well. And then I'm going to assume, I'd like to assume that there exists a constant, I'm going to call it K, that is strictly positive, such that for all x in D, the absolute value of f of x is greater than or equal to K. So this is a function that is bounded away from the x-axis, right? Prove that if I make a new function g of x, which is going to be defined to be 1 over f of x, that is also uniformly continuous on D. So I like this problem. This should be good. So you take the reciprocal of a function that's already uniformly continuous. And the idea here is to prove that that reciprocal is still uniformly continuous, provided that we have this extra assumption that obviously we wouldn't want f of x to ever be equal to 0. But this is actually, I want to point out, this is even stronger than that. I mean, I could have just, maybe I would have just said, could I have just said that as the assumption instead? I didn't say that. And that's because if you tell me that the absolute value of f of x is greater than 0, it still could be arbitrarily close to 0. And if that was the case, then this reciprocal function would be blowing up to infinity, right? Even though it might be defined everywhere, it would be failing to be uniformly continuous because basically it's going to have a vertical asymptote, right? So this is not as strong as saying that the absolute value of f of x is greater than or equal to k greater than 0. This is a stronger statement. This is sort of saying there's actually a buffer here. There's a barrier that the f of x has to stay on this side of that barrier. Okay, so you kind of see the difference? Yeah, okay, so that's a stronger assumption. But with that assumption, then hopefully we can prove that g of x is uniformly continuous on D. Okay, so let's think about how to maybe do this. Anybody want to tell me the first sentence? Get our rubber stamp out. Yep, let epsilon greater than 0 be given. And we ultimately have to come up with a delta. So just to remind you again, so for all epsilon greater than 0, there exists a delta greater than 0. This is the definition of uniform continuity, such that for all x and y in D with absolute x minus y less than delta, then if we apply it to our function, I guess in this case our function is g, the absolute value of g of x minus g of y should be less than epsilon. So this is g is uniformly continuous on D. That's the definition essentially. So again, this might be part A of the question, and to have you just write that down, that'd be worth some points, and then I'd give you this problem. Okay, so what we usually do in this situation is what I want to do here, which is to go to some scratch work to figure out the delta, right? Our job here is to figure out the delta. And anybody out there in Zoom, if you have any questions or if you can't see the whiteboard or something, just speak up because I can't really see it that well from my angle here. But just let me know if you're having any trouble hearing me or seeing anything on the board, okay? So I'm going to go here to the scratch. And I'm going to kind of work backwards from the ultimate conclusion that we want, which is that we are hoping to end up with absolute g of x minus g of y less than epsilon. Okay. So how can we kind of work from there? Well, sorry? Yeah, I mean, we have assumptions about f. So if I'm going to get anywhere with this problem, I need to rewrite everything in terms of f, which is what I have information about. So I'm going to rewrite g of x as 1 over f of x, and I'm going to write g of y as 1 over f of y. Okay, so that certainly makes sense to do. And anything in particular strike you here that we might want to do? Yeah, just do a little algebra or subtracting fractions here. So I'd probably make a common denominator. So the common denominator would be f of x times f of y. And then in the numerator, we would actually have f of y minus f of x. But I don't mind, since it's in absolute values, we could rewrite it as f of x minus f of y just as well. Be no problem doing that. Okay. And it's kind of good to see that showing up because we know that f is uniformly continuous, which means that given this epsilon, there already exists a delta for f, right? Such that blah, 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 absolute f of x minus f of y is less than whatever we want. Okay, so so coming back to the main proof, we could actually start to incorporate that. right? So since F is uniformly continuous on D, then this is where we're going to get our delta from, right? So there will exist a delta such that if X and Y are elements of D with absolute X minus Y less than delta, then absolute F of X minus F of Y is less than whatever we want to put here. Now, I don't know that we want to put epsilon here because the scratch work is not telling me that we're going to get epsilon there. In fact, maybe I'll go another step on the scratch work here. The scratch work is telling me if I solve it for absolute F of X minus F of Y, the scratch work is telling me that it's less than epsilon times absolute F of X times absolute F of Y. Now, am I allowed to put this right here? I'm not, because what goes right here, guys, has to be a constant, right? In your definition of uniform continuity, it's for all epsilon greater than 0, right? So what's going here has to be this constant value. And I don't have a constant here, right? So I can't just stick this over here. Now, if you get to this point and you're like, oh, I'm stuck, I don't know what to do, right? And you're taking a test and you're in this kind of a situation, I would say just leave everything the way it is. Just take a breath, maybe even go on to another problem, knowing that you've done a huge amount of the solution already just from basic algebra and knowing how to set up the definition. So the tricky step is really the only thing missing, but you can get lots of partial credit for having the rest of this filled in. So my question for you then is, if we can't put something that depends on X and Y here, what do you think we might want to do here?
Okay.
We haven't seen the K anywhere in the scratch work or in the proof yet, right? So that's part of our assumption. And the assumption here is, let's just look at it. Absolute F of X is greater than or equal to K. So could I take both of these guys, and this, by the way, that was for all elements of the domain. So could I take both of these guys and replace with K? Hi, just careful of my camera. So let's look at that. So I'm not going to put a logical connective quite yet, but it'd be great if I could replace F of X with K and F of Y with K. That would be great because this is something that we would be allowed to put right here. Now, the question is, does it work? Because remember that your scratch work has to work backwards, because this is ultimately the last line of the proof. And this is the second to last line of the proof, and so on. So this has to work backwards. Does it work backwards? This is what you want. I don't think it's going to work in both directions, right? So does this work? Well, let's see. If absolute F of X minus F of Y is less than this much, then if we replace K with F of X and we replace the other K with F of Y, we're only making this side of the inequality larger, which means if this was already true, then this would be true. It doesn't work the other way around. So this is a backwards arrow. Sometimes people don't put these arrows in their calculation, and that does get my red pen out, because these steps are not always reversible. Okay, so guys, this is beautiful. We can come in here and we can put that into our main proof. So absolute F of X minus F of Y is less than this expression here. And now what we can say is retracing our scratch work. So retracing the scratch, we conclude that absolute G of X minus G of Y is less than epsilon, which is ultimately what we needed to prove. So I'll just say as needed. Okay, so that's it. That's the problem. Okay. So any questions on that? This would be a nice question. Something kind of along that level, I think is a pretty good example. Okay. Well, if everybody's okay with that, I'm gonna go to another problem. I'm sorry, I'm shuffling around a little bit because I did some of these the other day. Just trying to make sure I'm doing, not repeating myself too much and finding the problems I want to find. I had another one. Oh, here it is. Yeah, I have another one that I really want to do. Can I erase? Okay, let's get this out of here, and I'm gonna do another problem that is also gonna involve taking a reciprocal of a function, but it's about a completely different topic. So, um, see, on this problem, guys, I didn't have the whole solution in my head when I started it, right? I had to just get the template up here, make sure I have my definition down, start writing my proof, and then just allow the scratch work to run itself. And then you get to a point where you're like, this is the sticking point. But you realize, oh, that's where the K comes into it, right? So you don't have to figure the whole thing out right at the beginning. Put down everything you do know at the beginning, so I can give you as much partial credit as possible. And then even if you don't manage to fill in every or connect every dot, you still have made great progress on the problem. And more than likely, you have a better chance of connecting those dots if you've actually started to write stuff out rather than just kind of winging it from the beginning. Okay, so that's just a general strategy for the exam. Let's do another problem here. This actually has two parts. Part A is give an example. Give an example of a function f, which is Riemann integrable on, we'll use the closed interval 0, 1 to make this nice, such that, so f is the function that we're talking about, and f of x should be greater than 0 for all x in the closed interval 0, 1. But g of x, which is going to be 1 over f of x, is not Riemann integrable on 0 to 1. But G should be defined on the same domain. That's the only thing. So we're talking about the closed interval 0 to 1. So this is the idea. We want to give an example of this kind of a thing. Hey, Brian. So I just did one example that was a really good problem. So I'll send out the video. You might want to watch the first 15 minutes just to see that example. Sure. And we're just starting the second one right now, which is this one right here. So any thoughts about what we might want to do? Maybe not what the final answer is yet or what an answer is, but maybe a strategy to think about something like this? Sorry, it's okay. I'm gonna just suggest maybe we try and draw a picture. Just kind of get a visual of what this might be, and then maybe we can come up with a formula for f later. But we're talking about just this interval from 0 to 1 here. And I need my function to be always positive, right? And I want it to be Riemann integrable. And we know a lot of things that are Riemann integrable. Constant functions, any continuous function, actually. A monotone function. Technically, again, that's not what this section of the exam is, but we know that fact, we can use it. So a continuous function, a monotone function, a function that has a finite number of points displaced from such a function. We even did that yesterday. So we know how to make Riemann integrable functions, that's for sure. Somebody was asking me the question the other day, well, how would you make a function that's not Riemann integrable? It seems like as our theorems have been developing, more and more and more functions are Riemann integrable, right? So anything that is a finite number of steps away from being either monotone or continuous, and it could be monotone on one subinterval and then continuous on the next subinterval, and then monotone on the next one and continuous on the next one, and you piece those together, it's sort of a big union. Well, that's still Riemann integrable. So what is a go-to way of ensuring that you have a function that's not, like, how would a function be not Riemann integrable? The easiest way, like basically the book is slammed shut, that it has no chance. Okay, that's the definition, right? The upper Riemann integral not agreeing with the lower Riemann integral. I want to go back even further than that, like to the very beginning of even having a conversation about whether a function is Riemann integrable. What was one of the assumptions about the function that we made? At the very beginning, the function had to be bounded, right? So if I could rig this so that G was not bounded, then it wouldn't be Riemann integrable. Now, I do have an assumption here that F is positive, which means that G will be positive. But could G be unbounded? If this denominator is very close to zero, it would be unbounded. Now, I say very close to zero, it can't be equal to zero, right? But it could be very close to zero. So could I draw a picture of a function that was always positive, but that, you know, became arbitrarily close to zero? Okay, so 1 over x would do this kind of a thing. All right, let's look at that example. So I have one problem with that. The function 1 over x is not defined on the closed interval 0, 1. It's defined on the open interval 0 to closed on 1. There's no value here. So what would you have to do? Yeah, you might have to define a value for f of 0, right? So you could try to create your function to be, 1 over x if x is positive. And then if x was equal to 0, you'd have to put in a number. I mean, you can probably put anything, probably just put 1, something like that. It has to be positive. So you could define that like that. Okay. So the question is that Riemann integrable? This thing is kind of blowing up to infinity here. So actually, if you might remember from calculus, this is an infinite amount of area under this curve. So this one is actually not Riemann integrable. And in fact, the problem more fundamentally is even this is not bounded.
Sorry, I think I meant like f of x was x, and then when you compose it with g of x, it turns into 1 over x.
Okay, let's start over. F of x equals x would be this.
Yeah.
Okay, and I have no doubt that that's Riemann integrable. However, I'm not allowed to use 0. So I'm going to need to put a hole right here, right? And then do something else. Maybe we can try this again. Okay, so now let's try that. So f of x equals x if x is positive, and it equals 1 if x equals 0. Let's think about whether that might work. See, now the reciprocal of this is unbounded. So in this case, so for this f, okay, so for f of x as given, note that g of x is unbounded on the closed interval 0 to 1. So g is not a Riemann integrable function on the closed interval 0, 1. But is f a Riemann integrable function on 0, 1? I think it is. If you wanted to make it even more obvious, what you could do is you could define f. Oh no, you can't use a negative. That's right. I'm sorry. So I think what I did here was probably just as good as anything. But the point is that this function, as we've defined it, is 1 point away. So we can use what we learned yesterday. It's 1 point away from just being a continuous and monotone function. So I'll just note here that also f is Riemann integrable on 0 to 1 since it disagrees at only 1 point at only, I'll just be specific, at x equals 0 with the continuous function, which would be, I'll just say h of x equals x for all x in R. So if you just make the line h of x equals x, that is continuous. F is almost the same function, it just disagrees with h at one point. So f is also Riemann integrable, and so you could finish your proof like that. Yeah, this looks real good. Yeah, that's a nice one. Okay, does everybody feel like they could come up with something like that? It's not too crazy. Okay, so I have a part B, if we're all good with the first part here. So let me state part B over here. We're gonna kind of fix this problem. So part B says, prove that if F is actually continuous on the closed interval AB, such that f of x is strictly greater than 0 for all x in that closed interval AB. Then, so if the function is continuous, if f is continuous and strictly positive, then the function g of x, which is 1 over f of x, is Riemann integrable on the interval from A to B. Okay, so obviously our example over here was not continuous at 0. So, but if we restore that, or if we impose that assumption that our function is actually continuous and positive, then the reciprocal is also Riemann integrable. Okay, so that is the problem. And what is our best method for proving that a function is Riemann integrable? We have the definition, but the definition is that the upper and lower Riemann integrals are the same, and those involve doing infimums and supremums of upper and lower sums. It's kind of a mess, because you have to think about arbitrary partitions. Is there a result that's a little easier to use? It was the theorem, I call it the characterization of Riemann integrability. It was, in the book, it's theorem 6.2, which is the one that says that for all epsilon greater than 0, there exists a partition such that the upper sum minus the lower sum relative to that partition is less than epsilon. So yeah, so that's exactly what I would do. I would use theorem 6.2. Remember, you do not have to know the theorem numbers. You can just say by a theorem from the book or a theorem from class. But we'll just cite theorem 6.2 in case you're referring to it. And then that theorem requires us to start off with let epsilon greater than 0 be given. And our job is now to come up with a partition. So let's come back over here. I need a little bit more room to do this one. So we have to find a partition such that UPF minus LPF is less than epsilon. Maybe we could even do some scratch work for that. We often do in this kind of a business. We have some scratch work that we have to think about. So this would look like UPF minus LPF less than epsilon. That's ultimately what we want to end up with. And I would recommend that we just put in what the formula is here. The UPF minus LPF, this is just a summation of a bunch of subintervals. So this gets a little technical.
Do we want it for F or G?
Oh, yeah, we want it for G. Thank you. Yeah, we absolutely do want it for G. We do want it for G. So this is actually interesting. F is continuous, and so F is Riemann integrable already by one of our theorems again that we just learned recently. So because F is Riemann integrable, there already exists a partition based on F. So maybe we could put that into our proof right now. Okay, so since F is continuous, on the closed interval AB. F is Riemann integrable on AB. Okay, that was, for those of you looking at the book, that's theorem 6.7. And so there already exists a partition in script P of AB such that U of PF minus L of PF is less than whatever we want to put into that box. Which at this moment, I don't know what I want it to be. I could put epsilon there temporarily, but I might have to tweak it later. The scratch work is going to dictate kind of what goes here. Okay, so meanwhile, we can come back over here and try to work backwards from where we're ultimately trying to end up with. By rewriting this as a summation of, now I'm gonna do this notation, guys, if you don't mind. I'm gonna write big M sub I and little m sub I, but I'm gonna be clear about whether I'm talking about F or G. So the big M sub I of G minus the little m sub I of G times delta xi. It's gonna be something like that. Okay, and I'm going to ultimately want to bring it back in terms of the big M's and little m's for F. So in fact, let's just go one step further here. This summation, back to the main proof. I hope this is okay. I'm kind of going back and forth between the actual proof and the scratch work, right? So this is going to be the summation of capital MI of F. So I'll use a little notation, putting the F in the parentheses, minus little mi of F times delta xi, and that's less than, again, whatever we ultimately put into that box. So I've got something kind of good here. This is what I want to end up with. Oh, I forgot to write less than epsilon here. Right, that whole thing should still be less than epsilon. But if I want to like get this to fit into the puzzle of the proof, I need the big M's and little m's to be relative to F, not G. Do we have any sense of how they're related to each other?
1 over big MI is gonna be the little MI.
Yeah, so guys, remember that G is the reciprocal of F. So the maximum values of F on a particular subinterval will be the minimum values of G, because you flip over a bigger number, you get a smaller number, right? So this function flips big M's to little m's and little m's to big M's. So I think what we could do here, guys, is we could rewrite this as little mi of F, actually, sorry, 1 over. So it's 1 over what would be the little mi of F minus 1 over what would be the big Mi of F times delta xi less than epsilon. So again, just to explain that really quickly, big Mi for G is the same thing as the reciprocal of the little mi for F. And little mi of G is 1 over the big Mi of F. So these little facts. Does this make sense? Yeah, it seems reasonable, right? So the maximum value of G on a subinterval would be obtained as finding the minimum value of F and flipping it over. Okay. So I got that in there. Any thoughts looking at that scratch work, what I might want to do? This kind of reminds me of the other problem, right? Because we're still doing a reciprocal function. If I make a common denominator here, my numerator is going to turn into exactly this. So that's going to be kind of helpful. Yeah, let's do that. So let's just do a little algebra on this next step, right? So the algebra would be to make a common denominator, and in the numerator of that, we'll have big Mi of F minus little mi of F. And then on the bottom, we have little mi of F times big Mi of F. All of that is still times delta xi, is still less than epsilon. You can see that the delta xi is just going to be in the background here. Nothing is ever really going to change as far as that goes. Okay, so we've got that and. But this isn't quite exactly what we have here. We have these denominator terms, and of course, those are all changing with I. It's not like these are constant values. So that makes it a little bit tricky. If I wanted to get rid of this denominator, which I kind of do. I kind of want this denominator not to be here because then I could just feed right into my proof here. I can't just get rid of that denominator, but I'm wondering, like, what could I do? So I'm gonna do a step that, remember, I only care about going this direction with my scratch word. So what I'm gonna try to do here, keep my less than epsilon, I'm gonna keep my numerator the same. I would like to replace this denominator with something that would be, let's get this right. A smaller denominator, because if this is a smaller denominator, then this fraction becomes bigger. And if this fraction can still manage to be less than epsilon, even after we've made it bigger, then it would certainly be less than epsilon when I make the denominator back to what it is here. So I'd like to make these denominators smaller. Are we clear on that? We don't want to make them bigger. Sometimes I get confused. Do I want to make this bigger or do I want to make it smaller? It kind of depends on whether you're upstairs or downstairs in your fraction. It's possible that in a weak moment, somebody could get that backwards, but don't let that ruin your day. I mean, your idea will, I mean, I might have to pull out my red pen a little bit, but it's not going to be like destroying the idea of the problem. So, in this case, we do want to make the denominator smaller in order to get this to reverse engineer itself. So can I make it smaller? And when I say smaller, smaller in a way that would be a constant. They didn't give us a constant, like in the last problem, there was a K. And we were able to just feed the K in there. They didn't give us anything here. They said f of x is greater than 0 on this closed interval from A to B. F is continuous. And we know that these little m's and big M's, they are just values of f on each of the subintervals. So they are among the values. So does f have an absolute minimum kind of a thing?
Let me see here.
What kind of an interval is that? It's a
Closed.
closed interval. What kind of a function is it? Continuous. What do we know about continuous functions on closed intervals? They have absolute extrema. Quite interesting. You wouldn't have expected this to be a relevant piece of this problem, but because of the assumption on f, right, we have so many results, don't we? If f is continuous on a closed interval, we have the fact that its range will be bounded, the extreme value theorem, the intermediate value theorem, location of roots. There's all those results that are all part of this exam. So yeah, I think what we can do here is we can say, maybe I'll just do it in the main part of the proof. Since f is continuous on this closed interval from A to B, what I'm going to say here, guys, is that there exists an alpha. In my solution, I call it alpha. There exists an alpha, and it will be a positive number because all of the f of x values are positive, such that f of x is greater than or equal to alpha for all x in the closed interval AB. Okay. It actually achieves this value alpha. In fact, there exists a C in this interval with f of c equal to alpha, such that f of c actually does equal alpha there. Yeah, hope that's all coming through on the video. Does that make sense? So there is an absolute minimum. It's the extreme value theorem, so this is theorem 4.2, I believe, that's the extreme value theorem that's allowing us to do that. And so what that means is that all of my little m's and even my big M's, both of them, they have to be at least alpha, right? So alpha is smaller than whatever these little m's and big M's would be. And so if I put that alpha here, I'm gonna do it twice because I've got two things here, right? If I replace the little mi with alpha, I'm making this denominator smaller. If I replace the big mi with alpha, I'm making this denominator even smaller. And if this denominator is smaller, then this fraction becomes larger. And if this fraction is larger and it's less than epsilon, then this fraction will be smaller, and so obviously less than epsilon. This scratch work will go this direction. I probably am. Thank you. Yeah, there's a delta xi there that just comes along for the ride. And the beauty of this now is you can move that alpha squared to the other side, and guys, that is what you want to put in your box back in the proof. Epsilon alpha squared. So you put that into those boxes and you can make this work. Technically, okay, there is one thing I don't like about this. I should have taken all of this epiphany right here and put it up. Yeah, I shouldn't be talking about alpha before I've introduced the alpha. So I probably should have even just put it right up here. I would probably just put it right there. So f is continuous on that closed interval, so there exists a c in the closed interval AB such that f of c is equal to alpha, which is the absolute minimum of the function. So now in my proof, it makes sense to write the alpha here. And so once I get to this point, then I can go retrace the scratch work. So retrace, scratch to finish. Pin myself into a corner here. I can't write to the right side of that line. Okay. Nice problem. It's a little tricky. Again, I could see people not recognizing the extreme value theorem playing a role here. But maybe with a hint, that would be something that would be pretty reasonable. Yeah. Okay. Yeah, like maybe that would be part A, state the extreme value theorem, and then part B would be use the extreme value theorem to prove this thing. Absolutely, that would be.
This is part C. Yeah.
Maybe you guys want to write my test for me. It'll save me a whole lot of time.
Yes.
You're happy to do, guys, you guys are all good with that? Okay, and it'll just be our little secret. We won't have to tell anybody about it.
Just don't let Jaden write it.
I would try, I would never do that.
That problem earlier, we had a uniformly continuous in the lower bound, you have those hypotheses here.
Yeah,
So,
yeah, exactly.
but you said the problem.
Basically just using it. Yeah. Okay, so where do I want to go from here? I guess I'll do this generalized mean value theorem problem. So I'm probably not gonna make a problem that uses this result, but I did state it in class and I didn't actually prove it, so we might as well do it. It's a good example to do. So this is number 9. So let's do the following. Let's prove the generalized mean value theorem, and I'm going to state it here for you. So it just says the following: let f and g be continuous on the closed interval AB. Those look like pretty standard assumptions for these kinds of results, and differentiable on the open interval AB. Then there exists a C in the open interval AB such that So here's the statement, and I did write it down a few weeks ago, but then we never came back to it, never really used it. I don't think it was in the homework, none of that. So we'll just take this as an exercise, not really something that's a main topic. So we're gonna prove this statement, that if we take the quantity f of b minus f of a times g prime of c, that equals g of b minus g of a times f prime of c. So there exists this c for which that is true, okay? And we can use the regular mean value theorem to prove it if we would like to. The trick to something like this is to apply an earlier result. It could even be just Rolle's theorem. In such a way that, but not to apply it to the little f or to the little g, but to something you're going to cook up as a new function. Whatever this new function is needs to have all the same assumptions, because to use the mean value theorem, you do need a continuous function on a closed interval and a differentiable function on the open interval. But for example, the Rolle's theorem would tell you that the derivative of the function at some point c is equal to 0. Do you see, now I don't see an equals 0 here. Would there be a way to create 0 out of what we have? Subtract it all over, right, exactly. So if I imagine kind of putting a minus sign here and then setting it equal to 0, that sounds good. Moreover, I also see maybe that the c is sort of the specific point where the derivative is being evaluated at. So I'm wondering if that would have been an x originally, that then, there exists a c such that when you plug it in, it becomes this. So the whole trick to this problem is just creating a new function. It's kind of not that different than the way we actually proved the regular mean value theorem, which is to construct a new function, which I'm going to call f, capital F. And that's in the spirit of the way I did the mean value theorem in class. Via. And so does anybody want to take a stab at it? Because this is really the key thing, is how do we construct this new function to which we will then be able to derive this thing. And this new function can be written in terms of little f and little g if you want. Remember, we were going to move everything to the left side. Also, f of b is just a number, f of a is just a number, g of b is just a number, g of a is just a number. We have no control over any of that, but those are fixed values. So you can literally think of this as a number times g prime of c minus a number times f prime of c. Any thoughts?
A number times f prime.
So let's just put this number down. That's just a number, right? And then times what?
F prime or big F.
Well, we're over here on this side for the moment. So this is f of b minus f of a times.
G prime.
So how about we put g of x there? Okay, because that's ultimately going to get substituted with the c when we apply the regular, we're going to apply the regular mean value theorem. And then minus the quantity of g of b minus g of a times f of x. Let's just try that. So this is just a scalar times g minus a scalar times f. So since f is continuous and differentiable on the closed and open intervals respectively, so is capital F, right? So I'll just make a note of that. Note that capital F is still continuous on the closed interval AB, and it's certainly going to be differentiable on the open interval AB, because it's basically made out of two functions that already have that assumption. So f and g are both continuous on the closed interval, differentiable on the open interval. So I can just make this function capital F, and because of those assumptions, I can apply the mean value theorem to this. Okay, so applying, this is the key idea, guys, applying the mean value theorem. There exists a C in the open interval AB such that, see, how does this thing work again? Capital F prime of C is supposed to equal, what is it? Capital F of B minus capital F of A all over B minus A? You know how that theorem works? Okay. While I'm erasing, maybe you guys can try to figure out what capital F of B is and what capital F of A is. Let's just see if we can do it here. If I do capital F of B, I'm going to get F of B minus F of A times G of B minus the quantity of G of B minus G of A times F of A. And let's see. Does that, I guess we could multiply this out and just see if anything simplifies. So this is F of B, G of B minus F of A, G of B minus G of B, F of A plus G of A, F of A. Well, I get 2 copies of the middle term being subtracted, but that doesn't look too good. So that's F of B, whatever that is, it's a number. It's some number. What about capital F of A? Let's figure that out. If I put in A everywhere I see, so everywhere I see an X, I'm gonna put A. Let's just see what this, if this gives me anything nicer. So F of B minus F of A times G of A minus the quantity of G of B minus G of A times F of A.
Dr.
Yeah.
And it shouldn't have been F of B on the end.
I'm sorry?
For big F of B, the last F of A shouldn't it have been F of B? Since
Oh,
we
did I
started
mess that
saying
up?
the B.
Oh my God, I messed that up. I did mess that up. This should have been, thank you. This should have been F of B. I sometimes make little mistakes on purpose. Just to see if anybody's listening. Okay, sorry. This is not right. So this is minus, but did you notice how I was just rolling with it? I was like, I'm just gonna keep going. We'll see what happens. Yeah, so now I'm gonna fix that. And is that gonna help me? Actually, it does, because this term does cancel this term. So it's a little bit helpful. Still doesn't look that great, but anyway, let's just keep going with this other calculation now. So capital F of A is, hopefully I got it right this time for this one. I'm gonna FOIL this out, expand it again, so we'll get F of B, G of A, minus F of A, G of A, minus G of B, F of A, plus G of A, F of A. And let's see if that cleans up at all. I see G of A, F of A twice. And then that's what we're left with. And I will let you guys catch up. Maybe you have any comments about it? This would have been really bad if I had not fixed my typo. I wouldn't have seen it. Maybe we can make a little space for John there. And we've got this camera here. I'm trying to not topple over. All right. Big crowd after all. So we are currently in the middle of proving the generalized mean value theorem. We're almost done. In fact, I would say we are done, but I'm waiting for anybody to tell me anything.
When you just put the F of B and the F of.
You wanna
A
put
back
those in there?
together,
Yeah, what's gonna happen when I do that?
Well, you're gonna lose some terms in there.
What terms?
You get the. what is
So I'm
it?
gonna have this and this minus this and this?
Yeah.
And what's that gonna give me?
Gonna lose the G of A, F of B,
G of A, F of B is here,
yeah, and you're gonna. subtract
but it's
the other
also
one.
here.
Yeah.
So those are gonna go away,
Mhm.
alright? And what about the other one?
It'll-
It also goes away. Yeah, that's the point. The point is that just by some miracle, note that capital F of A is equal to capital F of B. That's exactly right. So thus, capital F prime of C is 0, according to this mean value theorem here. Capital F prime of C is 0, but what is the derivative of capital F anyway? Because we haven't calculated that yet, I could take the derivative of capital F with respect to X. So this is my capital F of X, if I differentiate it with respect to X, keep in mind, F of B and F of A are constants. So that's just a constant times G of X, so the derivative of it is just F of B minus F of A times G prime of X. Minus, and then the second part, we also have the constant in front, G of B minus G of A times F prime of X, little f prime of X. And so last but not least, if I just plug in C where I have the X here, so we already know that capital F prime of C is 0, so if I put in C for X in this thing, it has to be equal to 0. So hence, last step here, guys, should be this should just be about it. We get F of B minus F of A times G prime of C minus G of B minus G of A times F prime of C, and that is equal to 0. And that ultimately proves our generalized mean value theorem. So that's the whole ball of wax. You have to kind of go out on a limb, well, you create this function, this is the hardest part of the solution, is just creating the capital F. But it's based on kind of looking at the formula we have here. Okay? And then you have to go out on a limb and just figure out, well, what are capital F of the endpoints? And just so happens they turn out to be equal to each other. So that's the magic of that. Now, see, what I could do, a good test question would be for me to change up this relation a little bit. Create something different, and then based on what I've created, that would then change what you would want to define here. But you would hopefully recognize that it looks like an application of the mean value theorem. You're taking, this is the mean value theorem right here, essentially. But you're taking a modification of it, the same assumptions. All the functions are continuous on the closed interval, differentiable on the open interval. We create some function that represents the thing we're trying to prove. And notice wherever there was a C here, down here, we put it as X, right? And where we have derivatives here, down here we don't have derivatives. If you just kind of remember that rubric for how to do it, then the rest of it should take care of itself. You have to trust the process that when you calculate these two expressions and sub them in here, you'll get what you want. Maybe it won't be that the derivative is equal to 0. Maybe I'll set it up so that F of B minus F of A is equal to 1. Right, and so then over here you'd have 1 over B minus A, and that would be part of whatever the relation was. So this is a tweakable example that you can kind of create, other problems for as well.
Would you do this on the final then, because you said this one you might not put on the exam?
I probably wouldn't put this exact generalized mean value theorem on this test, but the idea behind this problem I think is a nice problem. I think it's a good one. Yeah, I definitely wouldn't shy away from that. I think it's a good one. We kind of did one like this the other day as well, where we were proving, I don't know, the very first problem we did on Monday's review session, where we had like f prime of c equals f of b e to the sine of b minus f of a e to the sine of a all over b minus a times e to the sine of c minus f of c cosine of c. That was another one of these things where, oh, it looks like the mean value theorem, but just not applied to f, but rather some constructed function that we have to make up. So I guess that's what I'm saying is that the theme of this problem as well as that problem is the same, which is that you're applying the mean value theorem, but just not directly at face value to anything that's given in the question. You have to create something new and then apply the mean value theorem to that. Okay, so if you just kind of have that idea in mind, that is gonna get you a lot of mileage into kind of a game plan for what to do. Okay. Let's do another one. So I'll go on to number 10. Let me, I think I know which one I wanted to do, but I haven't done yet here. Ah, yes. Okay, so number 10. Here it is, guys. Everybody so far so good? Okay, people feeling okay? All right, so let's do it. Let's do f of x equals the arc tangent of x. Here we go. Everybody ready for some trig?
No.
No? Well, I promise this won't be that bad. Let's use, gives you a lot of reassurance, right?
I never believe you when you say that, Dr. Green.
I know, I should probably just keep my mouth shut. Use rules of differentiation to prove that f prime of x is 1 over 1 plus x squared. Oh, and this is part A. Yeah, this is part A. There's going to be a little follow-up as well. Okay, so we're talking about the arctangent function or the inverse tangent. And I want to take the derivative of that inverse function. So any thoughts about how we would do that? I mean, I could also ask you the same question with the logarithm. The logarithm is the inverse of the exponential function. And so if I want to figure out what's the derivative of ln of x, and they often will derive this in a calculus course. If two functions are inverses of each other, what does that mean about them? If f and g are inverses, one more time?
Opposite reciprocal slope.
Yeah, but I'm talking about just more fundamentally, what's the definition of they undo each other? Meaning, can you?
Like addition and subtraction now.
It's not addition, it's not subtraction, it's not multiplication, it's not division. What is it that we're gonna do to these two functions?
Yeah, we're gonna differentiate.
Compose.
Yeah, there you go.
We're gonna compose the functions, right? So we're gonna make another function, which is the one that cancels this one, that undoes this one. Let's do it. Let's define g of x to equal the tangent of x. Okay, so we create the function that is the inverse of the f, right? So then what we know is that if we take g composed with f of x, it's equal to x. This would be for all x in the domain. And I will just give you a freebie here if you're not super on your A game with this function. The domain of it is all real numbers. So I will just tell you that. So for all real numbers, if you compose these two functions together, you get x. Okay. My goal is to figure out the formula for f prime of x. So what is this having anything to do with?
The chain.
The chain rule. The chain rule. I'm talking about taking derivatives and I'm also talking about doing a composition. If those two things are in my head at the same time, bells should go off, chain rule, right? So the derivative of both sides. Let's differentiate. So on the left side, I'm gonna write it out longhand here. It's just g composed with f prime of x. And on the right side, we have a 1. the derivative of x is just one. And this is, again, for all x in R. And so now just need somebody to tell me the chain rule, because we have to plug it in now on the left side. So does anybody remember the formula?
Prime of x times g of x minus f of x. Oh, that's,
Are you giving me the definition of the derivative?
no, I was giving you.
The quotient rule?
Quotient rule.
Oh, okay, yeah, I don't want
I
the
was like,
quotient rule.
ignore that, just kidding.
Sorry, I want the chain rule. Does anybody remember the chain rule? One more time, sorry.
I'm just mumbling to myself.
Mumbling to yourself. Okay, does anybody think they have it? This is on your review sheet. Everybody needs to know this for tomorrow.
G prime of f of x.
G
times
prime.
f prime.
There we go. G prime of f of x times f prime of x equals one. I love it. Okay, great. So we've got that much so far. That's a good start. Let's come back over here. So I can actually solve for f prime of x right now if I want to. Might as well do that. So we'll just write it down. So what do we have? We have f prime of x is equal to 1 over, and I kind of like that because my formula is 1 over something. And then what we have is g prime of f of x. Okay, so there's how far we've gotten so far. So it looks like we need to know the derivative of g in order to make this, this is what we're trying to prove. And this is where we're at right now. So it has some promise that, I mean, it's got a 1 over, both of them. So it's just looking at this denominator. So I need to know the derivative of g, first of all. So if I have tangent of x and I want to take the derivative of it, does anybody know the answer?
Secant squared green.
Did you just have that memorized?
I work with high schoolers, so.
Oh, okay. You got that one down. What if you didn't know it off the top of your head?
Right, derivative of.
You do what?
I would just write the derivative.
Oh,
of
the
That's what I
derivative,
did on
just
the.
put the words
graph
down?
example.
Oh, okay, okay. This is, I'm gonna just tell you, guys, trig is not my strong suit. So anytime I see something like a secant or a cosecant or a tangent, I freak out, but there's something I do to calm myself down that always works every time, which is to
They're always sines and cosines.
rewrite them in terms of sines and cosines. When in doubt, you can do that.
Sine and you can do the.
You do need to know, I mean, I do expect people to at least know that the tangent of x is sine over cosine. Okay, so this becomes a quotient.
That one I did know.
And so believe it or not, you may have been reciting the quotient rule a few minutes ago.
Do it.
Turns out it is relevant. It is relevant right here. So I'll just remind you, it's the denominator, which is cosine of x, times the derivative of the numerator, which is cosine of x, minus, so low d high minus high, which is sine of x, times the derivative of the denominator, and the derivative of cosine is negative sine. Again, I'm playing this game in case we didn't remember. If you happen to remember that this is secant squared of x, then you're good to go, but we can also get it this way. And the numerator now of this fraction is cosine squared of x plus sine squared of x, which equals 1. Exactly. So this is just 1 over cosine squared of x. And so Brian was right. It's just secant squared of x. Okay. So the derivative of tangent is secant squared. I can now feed that into where I was up here. So my f prime of x is 1 over, so it's g prime of f of x. So that would be secant squared of arc tangent of x. So whatever the f of x was, I'm just gonna go ahead and put that in there. So this is the secant squared of f of x. This is more trig than we've done all semester. Okay. And somehow it's supposed to end up being 1 plus x squared. Does anybody know how that happens? You actually have to draw a picture in this class. I don't know if I've done that all semester either, but you actually have to do a little bit of geometry. Can you imagine Dr. Annan doing that? Where's Dr. Suchavo?
No, actually, I
Um,
can't, because I text you,
So
don't do them.
I'm gonna make myself a little triangle here, and I wanna get, I need my triangle to have, 1 + x² showing up somehow. So I can label the legs of this triangle in some manner that hopefully gives us something that we want. Maybe we have an angle here, just label theta for a minute. So I'm just doing a little side calculation. And so maybe I have x here and 1 here, and my reason for that is that our Pythagorean theorem gives me the hypotenuse, right, which would be what?
Plus X squared.
Square root of 1 + x². Excellent. Okay, so we have something like that. So, actually, I don't like the way I labeled the theta. I think for this, because if I want this thing here to be, say, theta, the tangent of theta should be x. So do you mind if I just switch those? So I'm gonna switch those around because in this picture, the arctangent of x is theta because, again, it's an inverse of tangent. So tangent of theta, from the picture, tangent of theta equals x/1. Remember that from trig? Opposite over adjacent. So tangent of theta is x/1. That means the inverse tangent of x will be theta. And now I just have to put in secant of theta squared. Let's see, secant is the reciprocal of cosine. What is the cosine of theta here?
Adjacent.
Adjacent over hypotenuse, that's 1 over this radical. And then I'm gonna be squaring it, right? Actually, you know what? Can I just make this easier? I have a secant squared on the bottom. Let's just get rid of the denominator and write it as cosine squared of theta. That way I don't have to think about fractions of fractions. Cosine of theta is 1 over the square root of 1 + x². And I'm squaring that according to the formula. And if I square a square root, I just get 1 over 1 + x². And that's what we were hoping to get. This is scaring everybody?
Yeah, do you really want us to write this on it?
The sample test had the derivative of tangent on it, and I just wrote the derivative of tangent.
Oh, you did?
Like,
Oh, okay, then you saw, supposed to use the quotient rule. Yeah, right. Okay, I gotcha. Yeah, so this is definitely a step up from that because it's using inverse functions. If I was feeling a little shaky on this, I would recommend you go home and try to derive the derivative of the ln of x. Because it works the same way. The ln of x is the inverse of e to the x. So you compose the two together, you kind of just run through the motions the same way. Do what?
Pulling out my calculus notebook.
You gotta do it sometimes. This is a calculus class, Oh, I have a part B before I erase too much. There is a second part to this. Where is it? Here we go. Yes, so part B. Without computing f double prime of x, I'm actually talking about the second derivative now. Without actually computing it, because we could compute it. You could take this thing and use the quotient rule and come up with the second derivative. But without doing that, I would like to show that there exists a C in the open interval from 1 to 3 such that f double prime of C is equal to -1/5. So, anybody have any thoughts about what this has anything to do with? We're not actually going to take the derivative, as it says, we don't want to actually compute it. What might this be relevant to? Which one?
IVT.
We've got IVT, the intermediate value theorem. What else do we have? Just the MVT, the mean value theorem. Both of those require us to have an interval. We do have an interval here. They gave us an interval, so we have an interval to play with. So we could, so the intermediate value theorem doesn't involve derivatives. The intermediate value theorem is just, okay, so if f of a equals this and f of b equals this, and I take a number in between, then there'll be some c value that hits it, right? By the way, we are required to have a function that's continuous. At this point, the only function on the board is this one, which is continuous. It's a rational function. Remember that rational function, you can just state this fact. Rational functions are continuous everywhere they're defined. In this case, this is defined for all real numbers because the denominator will never be zero. So we can certainly assert that this is continuous, and but if I only work with this function with the IVT, there will be no use of the second derivative. So to go from the first derivative, if I want to go sort of to the next derivative, that rings a little bit more of the bells of the MVT, right? So the MVT, right, is something about, I'm just gonna give you the short version here, right? You have your interval from A to B, and you can take whatever the original f of B minus f of A over B minus A, that has to equal f prime of C. So if I'm talking here about the second derivative, then, so let's see, how would you envision using the mean value theorem? To what function would you apply it?
To f prime of x.
All right, let's try that. Let's try that. So if we apply it, so we already know, so for the solution, note that f prime is differentiable and continuous. Of course, I don't need to say that because differentiable implies continuous, but I'll just say it anyway. Differentiable and continuous on all of R. Okay, so we don't have to get too tied up on what exactly the domain is. F prime is differentiable and continuous on all of R. So applying the mean value theorem to f prime on the interval from 1 to 3, then immediately what it says is that there exists a C in the open interval 1, 3, that's sounding real good for what I'm trying to prove, such that the derivative of my function, but see, my function is already the first derivative, so this would now become the second derivative of the function at C, and this would need to be equal to f prime of 3 minus f prime of 1 all over 3 minus 1. Okay? Can we figure out what f prime of 3 and f prime of 1 are? Sure can. You have the formula right here, right? So f prime of 3, if we put in 3 here, we're going to get 1 over 1 plus 9 is be 1/10, right? So that's 1/10 minus, and then f prime of 1 would be 1 over 1 plus 1, that's 1/2. So we have 1/10 minus 1/2 all over 2. I wonder what that comes out to. I bet it comes out to exactly what we want. Let's just check it out. This is really 1/10 minus 5/10, which is -4/10, and then you cut that in half, it's -2/10. Well, -2/10 is -1/5. That's the proof. That's the proof. So it's just an application of the mean value theorem. Again, well, we've seen that a lot in today's session. The mean value theorem is coming up. It's just another application of the mean value theorem, but this time to f prime. Okay, I don't think I've shown you one of those before, where you're actually getting information about the second derivative by applying the mean value theorem to the first derivative. Yeah, okay. So we did that. I've done that. What time is it anyway?
3:21.
Okay, great. May end up running out of problems. Because I did that during the group work. No, I've got, I think, one thing we haven't done in either of the review sessions is just one of these brute force Riemann integration calculations. Would it be okay to practice one of those? Okay, why don't we do that? Let's just come over here. And we did one in lecture, because I proved that the integral of x squared from a to b is 1/3 of b cubed minus a cubed. It's a little messy, but let's do one where we actually have some numbers to plug in. I think this is number 11 now. This will take a lot more of the board to write it all out, but let's do this. Let's let f of x equal 4x squared plus 1. And I just want to compute the integral from -3 to -1 of f from the definition. If I don't say from the definition, then I can get myself into trouble, because we do have a very easy way to do the integral. By the way, actually, what I would highly recommend on a problem like this is that you do kind of cheat and you go over here and say, well, I know how to do this. If I want to integrate 4x squared plus 1, I know that I can do an antiderivative, right? And evaluate it from -3 to -1 and come up with a number here. Maybe I should do it. -4/3 minus 1, and then I plug in the lower limit. Oh my goodness. -3 cubed is -27 divided by 3 is -9. -36, but we're subtracting that, so I think it's plus. And then I have a -3 that gets plugged in. I think that's also a plus. So this is going to be the answer. I already don't like this problem. 39 times 3 is 170. What?
38.
Oh, it's 38. Sorry. I cannot get this right. 38, but then I want to put it all over 3. So 38 times 3 is 114. Thank you. And I'm subtracting 4 from that, so 110 over 3. Okay, let's hope that can be possibly correct. Okay, so I just like to know what the right answer is supposed to be, so that when I do this, I'll kind of know. Now, truth be told, if you're taking the exam and you come up to the end and you don't have that, you probably won't have time to go back and do the whole thing again. So I would recommend not erasing it. I get shivers every time I watch students like erase an entire page of work, and I'm like, there goes all
So-
the partial credit.
If we start that on a page and then go, no, wait, I'm taking this home.
You could do that. Yeah,
Okay.
you could decide that this problem, so here's the thing, this problem is not that difficult to know what to do, right? Because you kind of know what the definition of Riemann integration is, but it's also time consuming. So you can make a decision. Do you want to save that time to work on maybe some other problems that require more creativity? Or do you want to just take the other problems home where it's maybe not as clear exactly what to do and just sink some time into this one? It'd be kind of up to you. I mean, I don't know if I'm gonna even put one of these on there, but if I did, you'd have to think about that. Okay, without further ado, I would like to, you can maybe sit here. Because I don't want to mess up my camera there. Good to see you. We're just starting a new problem. This is the 5th problem that we've done today. I really like the ones we did earlier, so I would recommend watching the video, which I'm hopefully getting. And I'll post that up in a little while. Okay, so guys, let's do this one from the definition. So what that would mean is that I want to calculate a lower sum and an upper sum. Remember how I kind of did this as a squeeze theorem, the application of the squeeze theorem? So we make these partitions, P sub n, okay? So so here's the solution now. this is the way I like to do this, for n in the natural numbers, consider P sub n, which is a partition of the interval from -3 to -1. And so in this case, I just can go ahead right away and put down what my delta xi's are. The delta xi is always b minus a over n, which in this case would be what? It's gotta be positive, so it's gotta be 2 over
Oh,
n.
yeah.
So it's just 2 over n for the delta xi. And then, I want to think about, I'm gonna draw a graph of this, by the way. This is a parabola that is comes down to a vertex at 1, but we only care about this part of the parabola over here. This part over here, right? And so this is where this is a little different than the one I did in class. I think the one I did in class was increasing. Now I'm taking one that's kind of going downhill on this arm of the parabola. So when I'm doing my big M's, I'm gonna be looking at the left endpoint of each. So I chop this thing up. The left endpoints are where my big M's are going to be. So maybe we should, before we even get to that, let's just remember how the xi's are defined. So you start with the a value, which in this problem is -3. And then you add 2 over n times I. So you add whatever the b minus a over n is times I. And this is where I goes from 1 to 2, actually starts at 0 technically. So I goes from 0 to 1 to 2 and dot 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 up to n. I always like to just sanity check here. If I put in I equals 0, I should get A. If I put in I equals n, I should get B. So I get -3 for the left endpoint, I get -1 for the right endpoint. Does all look okay? Okay, so my big MIs are going to be the f of, so like big M1, which would be the first subinterval, would be actually f of x naught. So it's a shift backwards by 1, so it's actually f of xi minus 1. And my little mi will just be f of xi. So you kind of got to get this part right. And that hinges on knowing whether the function was increasing or decreasing. I actually consider drawing the picture to be an important part of it. By the way, if the function was doing this kind of a behavior and your interval was down here somewhere, then you got real trouble. Because then your big M's and your little m's, they aren't always on the left endpoints of the interval. What you'd have to do for that is you'd have to chop the interval into subintervals where the function was increasing. So it's decreasing here, it's increasing here, it's decreasing here. And all of a sudden, this is way too long for it to be a reasonable question, right? So you shouldn't be surprised that I might create a function where it's clearly decreasing or clearly increasing on that interval so that you're not, I mean, it's already enough work to just do it with a function that's monotone. So if your function's not monotone, calculating the big M's and little m's becomes really difficult on a case-by-case basis. Anyway, so let's go ahead and just take this. So my f of xi minus 1 would be 4 times xi minus 1 squared plus 1. And the little m is just 4 times xi squared plus 1. So I'm just doing both of these calculations kind of side by side here at the same time. And we can plug in the xi expression too. So the first one, we have 4 times the quantity -3 plus 2 over n times I squared plus 1. And then on the second one, we would have 4 times the quantity -3. Oh, I've made a mistake. It should be I minus 1 up here. Sorry. 2 over n times I minus 1 quantity squared plus 1. This is the one that should be -3 plus 2 over n times I squared plus 1. There we go. Okay. Great. So with those things in place, I'm going to try to write down my lower and upper sums. Okay. Do you want to do the upper sum first or the lower sum first? Upper, okay, it does not matter, so I'm just trying to be accommodating. Let's do the upper sum first. This is just the summation, I going from 1 to n of big Mi times delta xi. I always like to get the delta xi factored out immediately because it's just gonna get in the way otherwise. So I'm gonna put the 2 over n on the outside. And then I'm left with a summation, I going from 1 to n of what we have up here, which is 4 times the quantity of -3 plus 2 over n times I minus 1 squared plus 1. Okay, and at this point, I'm gonna need more room, so I'll just keep coming down here. Right. It's a little messy, no doubt about that. Okay, so let's keep going here, guys. We have a 2 over n out in front. And then on the, let's just go ahead and put a brace here. I'm actually going to multiply this out. Right, so it's gonna be a little messy, but we're gonna have to deal with it. So we have a summation, I going from 1 to n. I'm gonna go ahead and feed the 4 into everything as I go. So -3 squared is 9, but then there's a 4 on that, so that becomes 36. So 4 times 9. And then there's a cross term. The cross term is 2 times -3 times 2 over n times I minus 1. And then there's also a 4. So let's get that carefully worked out. 2 times -3 is -6, and then times 2 over n, that's -12 over n times I minus 1, and then there's a 4, so that's 12 becomes 48. So 48 minus 48 over n times I minus 1 squared. If I've done that right, by any miracle, I don't like it. There should be an n squared, right, in the bottom?
No, because you're not squaring that thing, that's your middle term, right? So, yeah. Then the last
Oh,
term should be squared.
yeah, I see what you mean.
The last term should be the squared.
Yeah, and then, so then I have the last term, which is just this part squared. That would be 4 times I minus 1 squared over n squared, but then there's also another 4 out in front, so that becomes 16. Okay, and then I also see a +1 there. Can I just change this 36 to 37? That takes care of the +1. Okay, it's kind of messy. But we're rolling. Now we're rolling. So this is equal to, guys, 2 over n times, now let's start adding up each of these pieces. 37 plus 37 plus 37 plus 37, that's n times that we're doing that, so that becomes 37n. And then on the middle term, I have the minus 48 over n that has to be pulled out. And then what are we adding up here? We're adding up 0 plus 1 plus 2 plus 3 all the way up to n minus 1. So it's the sum of the first n minus 1 positive numbers. And that would be n minus 1 times n all over 2. Okay. And then the last part, I've got 16 over n squared. I'll copy that down first. And then what I have is 0 squared plus 1 squared plus 2 squared plus 3 squared. The sum of the first n minus 1 perfect squares. So I shouldn't have erased this line. So the summation of I squared from 0 to, well, let's just put n here for now. Let's just put 1 to n. Just get this formula.
Two n plus one.
Sorry, this should be n times n plus 1 times 2n plus 1 all over 6. You know what?
Two n plus one.
Oops,
You got excited.
I got excited. You know what? I'm gonna give you that formula. You don't need to memorize it. That's just not something you need to memorize. So Anyway, this is the formula we have, but I'm applying it not to n right now, but only up to n minus one, because if you plug in the top limit of the sum, this is an n minus one squared. So I have to take this formula and everywhere I see an n, I need to write it as n minus one. So I would get n minus one times n, and then the two n plus one would become two n minus one, and then all of that over six. Whew. There we go. Okay, and let's clean this up now. I'm gonna multiply the two over n through. So 74 minus, and then the twos cancel here, and I just have a 48, and I do have an n minus one on top, and there will be two n's on the bottom and one n on top, so I can partially cancel that. And then on this last term, I can take the 2 times 16, that's 32, and divide that by 6. That's 16 over 3, I believe, for the coefficients. And then I have 3 powers of n on the bottom, one of which can cancel with the n on top. The rest of what's on top would be the n minus 1 and the 2n minus 1, and we'd still have an n squared there. Look all right? Okay, so that's the lower sum. Sorry, the upper sum. Still have to do the lower sum.
Didn't ask that, 'cause you don't have n minus ones. Turn.
But let's do this. Let's just, I wanna get the big picture of how this works. The lower sum is always, as you know, less than or equal to the lower Riemann integral from a to b of f, which is less than or equal to the upper Riemann integral from a to b, which is less than or equal to any upper sum, including the one we just calculated, right? Let's look at what happens as n goes to infinity here. I just want to kind of jump ahead to where we're going with all of this. As n goes to infinity, this expression is a 74, and then minus, guys, when n goes to infinity, n minus 1 over n just becomes 1. Right, it's really 1 minus 1 over n, so it just goes to 1. And then here I have a 16/3, and did I? Yeah, okay, I have a 16/3, and then I'll have a 2n squared over an n squared. That's just a factor of 2. So 16/3 times 2 is 32/3. And I'm just curious what this is equal to. This is 26, so 74 minus 48, I believe is 26, plus 32/3. If I make a common denominator by putting a 3 on the bottom, 78. Yep, 78 plus 32. Miracles happen. 110 over 3. That's what we're expecting it to be. Okay. So maybe we can skip this one, or would you like to do it?
By the squeeze theorem.
The only difference is that right here where you have an I minus 1, this will turn into just an I. And what that will do is turn this into an I, turn this into an I. So this will be n times n plus 1. This will just be n times n plus 1 times 2n plus 1. But all those extra factors don't matter. The only thing is that as n goes to infinity, this is still going to be the same. This is still going to be the same. So this is going to converge as well. And because of that, viewing this as a sequence that's between these two, it must converge to this same value. But since it's a constant, the value of that constant is that value. And same thing for this one. Okay, and so therefore the two integrals are equal to each other. Okay. Yeah, so these are a little tedious. They're a little tedious, but they're not really that difficult from a concept perspective. You just have to be careful with it. So I'd ask you if you want one of these on the test, but I don't know if you do or not. That doesn't matter. I haven't thought about the test yet.
Well, if you were to put this on the test, it wouldn't be enough just to show the upper sum, right?
Well, I could rig my question. I could rig my question and say calculate u of p sub n of f, and just leave it at that. And then I could make a part B where I say, by the way, the L of P of N of F formula is this. use that to prove that f is Riemann integrable and find the value of the function. So I could do that. I probably would do that, actually. It's unlikely that like, my goal is to see you demonstrate as many things as I can in a 2-hour time frame. If we've already spent, I don't know, 15 minutes or something doing this, I don't really think having you spend another 15 minutes doing basically the same thing again is really the way I would feel good about a test question. So more than
Can you
likely.
give us a pretty simple one for the homework? The
Yeah.
Homework, the f of x equals.
I
X.
could make an easier function
So that
too.
it's like,
The fact that that's squared definitely makes it tricky. So if I could come up with something. I have to come up with something that it's clear what the big M's and little m's are. So if I was to do, oh, well, let's just do f of x equals 2x plus 3 over 5x plus 7. I mean, that looks wonderful, but I'm not gonna know, like, since it's a weird fraction where both the moving parts on top and on the bottom, it'll be hard for anybody, including myself, to figure out where the big M's and little m's are within my subinterval. So I'm probably not gonna be so fond of a question like that. It's not my goal to, like, give you something where you can't really effectively demonstrate the knowledge of the material. So that would not be a good question. This one's okay, because at least it's a monotone function where you can write down the big M's and little m's easily. From the nature of the interval that I gave you. But again, if I used an interval that passed through 0, that would be really tough, right? At that point, I could ask you a specific thing though. I could give you the interval from -1 to 2, and I could ask you to calculate u of P8 of f. Get real specific, so then you'd have to come in here and chop it up, and then you'd actually have to look and see, oh, well, for the M1 and the M2, I'm using the left endpoint. And then starting with M3 and M4 and M5 and M6, then I need to shift to the right endpoint for the big M's. Because I can see if I would have to set this up perfectly so that on each little subinterval, everybody would be able to figure out which endpoint is the big M or the little m, or is it somewhere in the middle? Like maybe I would set it up so that this vertex is somewhere in the middle of, say, the 5th of the 8 subintervals. Like I could really, like, pin this thing down. But I would have to be careful with that and make sure that it was something doable. Yeah. If I had this interval straddling 0 and I didn't give you, and I just wanted Pn, now now you don't know where is this critical vertex, like which of the subintervals is it on? And when do we switch from the big M's being the left side to being the right side? That would be very difficult to sort of provide a general answer for. And it would not be a good test question, to be honest with you.
What's the one we did where we were doing the big M, little m in pairs and they were canceling out? And we were just left with the first and the last.
That was for a monotone function. Yeah, that was for
But linear.
it didn't need to be linear. In the homework, you did e to the x. And e to the x is monotone and the argument works the same way. The thing with that though, John, is that on that problem, we were proving that the function was Riemann integrable only. We were not actually evaluating the integral. If I wanted to have you prove that this function is Riemann integrable from -3 to -1, then I don't actually need to calculate UPN of f and LPN of f. I can just look at the difference. Because I know that the big M's and little m's are gonna cancel all throughout, and I'm only gonna end up with, the big M1 minus the little mn. And I can, without writing out all this messy stuff, I can just say, oh, well, this stuff's all gonna cancel anyway, so let's not create a headache over that, right?
When we use
But-
theorem 6.2.
That was theorem 6.2. We were using theorem 6.2, is on this most recent homework, I think it was problem 5. If I only am asking you to prove that the function is Riemann integrable, and if it's monotone, like this example is right here, then yes, you can make your life so much easier by just doing that telescoping cancellation. The issue comes in when I actually wanna know what's the integral. Yeah, at that point, it's another step beyond just because then you really need to do this thing. And for that, you really need to have your upper and lower bounds on it. Yeah, good question, real good question. Okay, okay, yeah, I'm just checking. I don't know. What else I wanna do? Oh, there was one more thing, where was it? Ah. I bet you guys are gonna be able to do this one, but let's do one more, guys. This one will kind of end on what I think will be a light note. Famous last words. I feel like we've done a lot. Oh, there's one more, on uniform continuity I want to do too. Anyway, let me start with this one first. This might go quickly, we'll see. So what I wanna do here, guys, is give an example. Number 12, give an example of functions f and g that both go from some interval a, b to r such that f times g is Riemann integrable from a to b, but f and g themselves are not. So you can have two functions that are not Riemann integrable, but then their product is. So this is maybe worth taking a minute to think about. We talked earlier about creating examples of Riemann integrable functions and non-Riemann integrable functions. The easiest way to have a function to be not Riemann integrable is if it was unbounded. However, in this case, I am using a closed interval. And so if the function was continuous functions on closed intervals are always bounded. So you wouldn't be able to create your example out of a continuous function in this case. But there is another sort of, I think we've seen it in class, an example of a way to make a function where it's perfectly bounded, but it's not Riemann integrable. Remember, if it's Riemann integrable on pieces, you'd be able to union those intervals together and get it to be Riemann integrable on the whole domain. So it's not gonna be easy enough to just say, well, let's just chop up A, B into 5 pieces and do something.
You do like if it's in R versus if it's in Q and it's kind of like opposite to where when they multiply, then it's constant.
Bingo, that was exactly what I was thinking. The idea is to use rationals and irrationals. That technically that's also a piecewise construction, but it's not like there's just 2 pieces that are like intervals. Now you have a domain that is constantly, these rationals and irrationals are densely interlaced within each other, so you are going back and forth between which case you are examining endlessly many times, right? So yeah, that's exactly what I would do. I would just let f of x equal something in the case when x is in Q, and then something else if x is not in Q. So this is a good way to do it. And you could just do something like, I don't know, how about just 1 and 0? So now I would want you to justify why is that not Riemann integrable? And the point would be basically for every partition, emphasis on every, for every partition, the U of PF would be, what would it be equal to? Let's write it out. It'd be the summation 1 to n of big Mi delta xi. So all of the big M's would be 1. And so you pull that out. And what's the sum of the delta xi's? B minus A, yeah, so it'd be B minus A. And at the same time, what would be all of the lower sums?
Zero.
Those would all be 0, because all of the little m's would be 0. So these don't agree at all. So the infimum of the upper sums, which is our upper Riemann integral, that would be B minus A. Whereas the supremum of all of the lower sums, which is my lower Riemann integral, is equal to 0. And these two things are not equal to each other. So you would be able to say, thus f is not Riemann integrable from A to B. It's a nice way to do that. And then you could just create another function g. So that's the story about f. Now what about for g? You could create another function for g in a very similar manner. So how would you want me to do g of x, guys?
Just swap the 1 and 0, right?
Yeah, just swap the 1 and 0. I think that would work. So this would be 0 if x is rational and 1 if x is not rational. And in this case, you could just say similarly, g is not Riemann integrable. Okay, so similarly, g is not Riemann integrable from A to B. Okay, so both of my individual functions are not Riemann integrable from A to B. However, what is f times g? In other words, what is f of x times g of x going to be equal to?
0.
For every x, it will be 0 because either f will be 0 or g will be 0, right? One of them will be 0. So this is just 0, which is a constant. And we had a homework problem where we proved that constant functions are always Riemann integrable. So which is in the Riemann integrable functions from A to B. So there's a good example for that. Yeah, so this is a way to create non-Riemann integrable functions without using any idea of boundedness, right? Your function's clearly very bounded here. And so you can do that. I would have to think about it, whether I could make an example where the f and the g are not bounded. But then f times g is Riemann integrable. So it would have to be two functions that are both failing to be continuous and trailing off to infinity somehow. I'd have to think about it. It certainly would not be anything that could be easier than this. So that would be a harder problem, but it's something to think about. So. All right, guys, I think I've done what I can.
The uniform.
Continuous?
Oh, there was one. Did you want to see one more problem?
Yes.
There's no limit to how I could stay all day, guys. Let's do one more. This one is also, I think this won't be too bad. So let's try one more problem.
Sorry.
It's for our class. Do you have a session in here?
Oh, no, I'll just send it.
Okay. I love watching the people walk by and they're like, what are those guys talking about?
That's how I feel sitting in the class.
There you go. All right, let's do this, guys. Let's prove that f of x equals x to the 4th is uniformly continuous on the interval from -1 to 2. So I didn't have anything super crazy to offer to you, but just this would be a standard problem. Standard example. Okay. So, what is the first sentence of my proof? Actually, let me slow down. You could give a fast answer. the fast answer would be what?
If it's on the
It's
form,
uniform.
It's continuous.
continuous on a closed interval.
Continue, and why is it continuous on a, why is this continuous?
Because it's uniformly continuous.
Oh,
No, don't go in circles. I haven't proved that it's uniformly continuous yet, so I can't use that.
Oh, because the function's
Oh,
on.
it's a polynomial.
It's continuous on a closed interval, why?
It's a polynomial.
Because it's a polynomial.
Yeah.
Because it's polynomial, so all polynomials are continuous. So this is continuous on a closed interval, therefore by theorem 4.4, it's uniformly continuous on that closed interval. So that would be the fast answer. So I'll just say solution number one, use theorem 4.4. I won't go into the writing all of that out, but you'll have the idea, I think, from that. Okay, but let's actually do the second solution here, which is to use the definition. And if I'm gonna use the definition, what is my first sentence going to be?
Let epsilon be greater than.
Let epsilon greater than 0 be given. Awesome, okay. And then I need to do some scratch work probably, so let me make myself some scratch space over here. And by the way, we started this review session with a couple of problems on uniform continuity. So for any of you who came in late, I would highly recommend those problems as well. This is just another example. Okay, so the scratch here, guys, is gonna be that, what do we need? We need absolute of f of x minus f of y to be less than epsilon. That's ultimately where we're headed with this. And so the first thing you might do with the scratch would be what? Plug in the function. I think so too. So that's just absolute x to the fourth minus y to the fourth less than epsilon. Okay. So here's where we're at. And does anybody have a thought about what we would do with that? We want to try to factor this one, right? So x to the fourth minus y to the fourth, that factors as x squared plus y squared times x squared minus y squared, which I'm gonna write as x minus y times x plus y. Oh, you have class, don't you?
Yes.
So this is the new inequality that we have. And let's just remember, the idea usually is to isolate absolute x minus y. So we go ahead and move everything over to the other side. Let me know if I'm going too fast here, guys. But I just like to get that x minus y by itself. Now, this unfortunately cannot be my delta because it has x's and y's in it. So I need to replace this right-hand side with maybe something that would imply it. So I'm gonna be assuming that I'm gonna have a backwards arrow here. And to make this work, I have to put some actual constants here. So my question would be, what would I want to put in? I need to put something in here that if this is true, then this one would be true. That means that this right-hand side should be smaller than this right-hand side. Is everybody with me?
Plug a bunch of twos in.
Yeah, so the trick is to plug in the right thing, because sometimes people will want to plug in the other endpoint. It's like, which one do you plug in? This is another one of those things where if you got it wrong, I'd pull out my red pen, but I'd be pretty gentle with it, right? You would want to plug in the biggest numbers that you can to make the denominator, the bigger this denominator is, then the smaller the fraction is. And if x minus y is less than that small fraction, it'll surely be less than something that's not quite as small. So I'm gonna make this into 2 plus 2 times 2 squared plus 2 squared. You literally can put that in there. Now, if this had been the interval from -3 to 2, for example, if it had been -3 to 2, then you would have been wanting to put in -3 everywhere. So -3 plus -3, that'd be 6, and then you'd have 9 plus 9 here. So it would be a slightly different calculation. But in this case, to make that denominator as small as possible, I want to put 2's in there. And what does this come out to? 32, right? Yes, that's 32. So what I'm going to do now back in my regular proof is I'm going to let delta equal epsilon over 32. All right, and now I can assume, if I want, I'll just assume that absolute x minus y is less than delta. And thus, absolute x minus y is less than epsilon over 32, and now I'm ready to retrace my scratch work. So retracing the scratch gives what we want, which is that absolute f of x minus f of y is less than epsilon. So the key thing here, guys, is that the delta cannot depend on anything other than epsilon. So I've got my epsilon in there, and that's okay, but it shouldn't have anything that is a variable in there, like a x or a y or a c or anything like that. So that was all. I just thought I'd do one of those. Obviously, I have to give you something that's factorable. You got to be able to get this x minus y out of this expression. That's probably why I chose that function. But if it's too crazy of a function, obviously this won't work very easily by hand. If I gave you some incredible f of x over here, right? Then starting from your scratch work and then how am I going to get x minus y out of it? You know, you could study for this exam for 500 hours and it wouldn't make that go any better. So that's not something to worry about. That's really just factoring issues, which is not what 350 is really focused on. So as long as you kind of have the technique figured out here, I think you're probably going to be pretty good on that. Okay, I just thought I'd do one more of those. The one that I did at the start of the review today was, I think, maybe even a little bit better example of this. So I will get this video compiled and loaded into YouTube, and within an hour, you guys should have an email from me with a video to watch if you're interested. Anybody have any questions? Thanks for coming. Appreciate you being here. Yeah, that ended up being a pretty good turnout. All right, I'm gonna stop this recording. Thank you guys in Zoom for coming. I'm gonna sign off, okay?